The regeneration of Hulme began in 1992 with the Hulme City Challenge, where it was decided that the area needed to be rapidly improved. There were 10 design principles which outlined the redevelopment process, and the Hulme Arch Bridge potentially covers at least 6 of these principles. A predominant principle was to create a landmark for the area to add interest and excitement, and another was to make the streets more than just areas of traffic, both of which were achieved by adding such a large and complex feature to Stratford Road. The purpose of this bridge is to allow people to cross the highway, Princess Road, below, safely and with ease. When Princess Road was constructed, it cut off access directly from Hulme to Oxford Road, so the Hulme Arch literally bridged the gap between these communities. It is both a car and passenger bridge in a busy area. It is wide enough for a lane in both directions and a pavement on both sides, giving a total deck width of 18 metres, and it spans a total length of 52 metres. The bridge successfully does its job, is aesthetically pleasing, and has won many awards, including IC Merit Award for an outstanding example of civil engineering work completed in the Northwest in 1997, bringing about positive news and coverage of the area, as opposed to that of poor housing and high unemployment rates. The asymmetry of the bridge allows it to be viewed at different angles and in different forms as the users cross it, making it interesting to look at. The arch spans diagonally from one side of the road to the other, so a moment is produced by the horizontal components of the tension in the cables on either side of the deck. These forces balance each other for horizontal equilibrium, but produce a moment. This is balanced by moments in the opposite direction in the fixed supports at the ends of the arch. This is a road bridge, so it has to be able to carry the load of heavy traffic. The bridge is 52 metres long and has 2 lanes of traffic, so assuming the average length of a car is 4.5 metres and the gap between cars and heavy traffic is 1 metre, there could be up to around 18 cars sat on the bridge at any one time. There is also pedestrian access to the bridge, so let's assume that 10 people are on the bridge together with all the cars, as well as the drivers of the cars and one person on each. That's a total of 18 cars and 46 people. Assuming the weight of a car is 20 kilonewtons and of a person 1 kilonewton, this would create a total load of 406 kilonewtons. The bridge itself weighs 365 tons, the majority of which is in the arch, so let's assume that the deck weighs 150 tons, 1.47 meganewtons. This would mean a load on the cables of around 1.88 meganewtons. We return to our calculations for tension in the cables, which we found to be W over 22 in the case of a vertical cable, and none of them actually are vertical. This would be 85 kilonewtons. In reality, it's the vertical component of the tension in the cables that must be this magnitude, so for the cables that are more sloped, small theta, the actual tension will be greater. The total weight of the bridge plus maximum load would be 365 tons, 3.58 meganewtons, plus the hypothetical load of 406 kilonewtons, for a total of 4 meganewtons. This is shared between the 2 ends of the arch, which sit on concrete blocks, therefore each supporting under compression a maximum load of around 2 meganewtons. As its name suggests, the Hulme Arch Bridge uses an arch structure to support its load. Arch bridges have been in use for thousands of years as they are simple and effective. This is an example of an arch bridge whose deck doesn't sit above the arch as is common, but rather hangs beneath it, suspended by cables. This is useful as it allows for more room underneath, and also allows the use of a large arch on a low bridge. The load on the bridge is transferred into tension in the cables, then compression in the arch, and then into large concrete slabs on the ground via the supports at either end of the arch. Assuming that the support reaction on either end of the deck is small compared to the support reactions on the arch, almost all of the load of the deck is transferred vertically into the cables. This means that the sum of the vertical components of tension in the cables must be equal to the weight of the bridge deck and its load. There are 22 cables, so 22 times T sine theta equals W. Therefore, T equals W over 22 sine theta. The tension in the cables therefore varies from cable to cable, as they are positioned at different angles relative to the bridge deck. Sine theta varies between 0 and 1, as theta goes from 0 to 90 degrees. So T will be largest with small theta, or in the cables with the least steep gradient. These diagrams show the shear force and bending moment distributions for the bridge deck. They were created using MATLAB under the hypothetical load discussed earlier. On the shear force diagram, we see a gentle gradient which is caused by the distributed load of the bridge under self-weight. The point loads are the tension in the cable, and as you see, they are all equal. The bending moment diagram shows a gentle parabola, which shows that the bending moment varies from 0 back to 0 along the length of the deck. The Hulme Bridge is a steel arch bridge, one built so that it can take the load of passing traffic or pedestrians that travel across it. The steel used to construct the arch is the S355J2 structural variant, which has, as the label suggests, a minimum yield strength of 355 megapascals. In total, there are 22 steel cables that hang in tension from the arch and support the weight of the bridge, each of them being 51 millimeters in diameter. So why use steel? Why not aluminium? Looking at the character traits of both materials, aluminium would seem like the better option to build the Hulme arch bridge. It's a lighter material, corrosion resistant, and often cheaper by the kilo than steel. However, the use of steel in the construction of the bridge can be attributed to its high Young's modulus, which means it won't deform under small loads. This being a disadvantage of aluminium, making it a suitable candidate for a bridge that would take varying loads. To make the steel arch more corrosion resistant, it was coated in aluminium paint, making the best use of materials. The weight of the steel used in the bridge is 365 tons, this equating to about 46.8 cubic meters of steel. The reason that steel was used in the construction of the bridge is because it's a tough, strong, durable material that when coupled with concrete becomes a compound that resists compression and tension very well. The change in length of the longest cable equates to about 1.66 times 10 to the minus 3 meters under normal loads and a full bridge. The points where the cables meet the arch show that the connections are pins. This kind of support allowing both vertical and horizontal reaction forces. The reason being that if the cables were rigid and allowed no movement, the small changes in the positioning of the bridge would produce large strains on the cables and possibly cause early failure. At what point would the cables fail? What magnitude would be required to break the cables? We see that the force required is about 50 times the normal load.
One of the Oxford Dictionary definitions of bridge is something intended to reconcile or connect two seemingly incompatible things. This bridge achieved the structural definition of carrying a road across an obstacle, but in many senses it also achieved the figurative bridging of Hulme to the rest of the city after it had been cut off by roads and passageways, making it a stronger neighbourhood. The main aim of Hulme's regeneration was to reintegrate it with the city and surrounding areas, and the Hulme Arch meets this completely in a physical sense and allows for a greater social connection by providing improved access to other communities.